program here, and it's called Cooling Library. We will loan equipment, thousands of dollars worth of coolers for free. Those of you who are familiar with energy centers, if you raise your hand, if you actually borrow a tool from this program before, okay, whatever. Yeah. So this is a really unique program. I want to say, I just actually reached out to Danny McNulty with Local 39, the big change in Virginia, and I mentioned to him the schooling library will actually be very quickly. Again, should be need to exit the flyer. You can also accept the front of the building, and what we'll do, that included, will convene at the corner of 4th and Howard Street where the carousel is located. So again, who knows where the carousel is? So follow these people, they know the carousel. I'll meet you there. Whether we need to expand the class for the day or reconvene. So that's our sort of exiting in case of emergency protocol. Now, how many of you are CPR certified? I am. So Shane will be our Shane call 911. I'll be our initial CPR provider. We've got registration that should be needed. And the other
somebody that we're trying to target around this. And the idea of step up and power down is really captured in this sentence: small actions for big savings. So I think of PG&E's office, as we look at our office facilities, how can the employees who come in and every day work in the office do very small things, turning off monitors, turning off the light switches, doing those best practices daily, although small watts individually, collected across our building portfolio, big savings, and then across the community, even larger. So small individual actions on the building occupants can add up to large savings for those buildings, and then even larger for the communities. And that's the side of the building operators and chief engineers, you all. So we're doing some, typically we keep it real traditional. These are some of the things that we've been doing so far, including a coffee tour to promote it. You may have seen our logos on the side of some of the buses within San Francisco and San Jose, and then also displays on the streetlights. We've also been doing some paid advertising on the online, which has helped generate more traction and help spread the word about the initiative. So the big part of it, one of the big components of it, again, is for the tenants of the buildings, and how can we teach them best practices? How can we get the people who use the equipment to do things that you, the building operators, want them to do? So one example here is we had a medical facility that had laboratory hoods, and the building operators there know that a big energy waste is through the fume hood. They have sashes that open and close, and the fume hood is pulling conditioned air out as they're testing. And so as a lab operator, I really only am concerned about the operations of my test and my use of that lab space. I'm not really thinking about the energy savings of reducing the conditioned air loss. But as a building operator, that's my big concern. How can I get people to do that better? So we ran a campaign with them called Adopt a Light, which was tailored to adopt a hood, which gives a personality to a piece of equipment. Behavior science says that if we can give that to a piece of equipment and teach that across the team, people will be more invested in it and be better users and stewards of it. So through this campaign, which ran 6 weeks, each were adopted by the team. They spread word about it, and the overall campaign was to reduce the amount of time those sashes were left open, mitigating the amount of conditioned air that was pulled out. As a big success for this customer. So that's the type of campaign that we are trying to launch. We are launching with these customers. Innovative approaches. Another is a vampire campaign, which is tailored at plug loads, trying to reduce the amount of loss through plug loads, educate employees about what's happening there and get them to use those in a better way, or install new equipment like a plug load occupancy sensor where possible. Tag Your It is another one, which is leaving behind recognition for savings opportunities. It'd be a small team dynamic, peer-to-peer behavior science, to engage those, educate my fellow teammates about it, and get them to be better stewards of the equipment that they're touching on a daily basis. One of the innovative things we're offering for customers to step up and power down is an energy practices inventory, colloquially a behavior audit, in which we'll talk to your tenants, ask them about past campaign successes, past campaign failures, and model these types of campaigns around what works and what hasn't worked in the past. What motivates the employees to participate in campaigns. So it's a series of interviews that we talk about company culture, proper motivators for the employees, and again, to learn from those historic successes and failures. Participation to date. So we have, since summer of 2015, we've been out recruiting customers for the initiative, again, in the large commercial space and also in the small and medium customer space. You can see our participation numbers so far. We've met our goal for San Francisco, and also we actually just met it for San Jose. We're really proud to announce that. Here's some pictures of small, medium businesses, large business operators who have been participating in it. Each have their own unique tailored campaigns that they run, tailored around the occupants and users of their space. So you can kind of see the enthusiasm and the community aspect of it. And that's it for Step Up and Power Down. Any questions?
Any of those educational for the tenants that you know owners of the building use that for education?
I haven't seen it used. So do building owners use those educational campaigns for lead points? Not to my knowledge that I've seen. That is a good point. I'm not real sure the lead criteria or if you can get points for that. But if it is an opportunity, that'd be great for them to highlight and get some of those extra points for.
One of the items there was moving refrigerators, mini bars. And forgive me, go to Ohio and Hotel, it has a mini bar.
So the question was, one of the opportunities highlighted was removing mini bar refrigerators in a hotel. And in that particular case, we had done a series of interviews with the hotel staff, the cleaning service that actually does the cleaning, and we said, what kind of savings opportunities do you guys see? And they said, the mini bars. Customers never use them. They sit completely unused, and we see that as a real big savings opportunity, is that in my daily cleaning of hotel rooms, I almost never see those pieces of equipment used. So they highlighted that as people on the ground, day in and day out, using the facility, highlighting a great savings opportunity that management maybe hadn't thought of, so it's a good opportunity to explore. So it's not us saying you have to remove the mini bar, it's just saying that your own staff is saying, day in and day out, they see a savings opportunity here. Let's explore it. Great question. Thank you.
Any other questions for Shane? So I just wanted to
Okay, so testing, can everyone hear me?
Yeah, we test with the online folks
Okay,
too.
good.
The online people can just verify that you can hear Doug.
All 1 million of them? Yeah. Does that work? Yeah, that works.
Let's do that again.
Okay.
If you can, if you're an online participant, just acknowledge that. Go ahead, Doug. If you can hear Doug, please just use the chat window to verify. Thanks.
Yeah, can you hear me online? Testing 1, 2. Yeah. Maybe I'll use that one. Can I hear you? No, no worries. All right, the people online, can you hear me now? Okay, good. Good. Thank you. All right, well, thanks everyone for coming. I was honored to ask to speak on behalf of this program and on behalf of Transamerica, also on behalf of my profession as a chief engineer. Being a chief engineer, I'm not a public speaker. So I don't have anything that's really scripted, but I have a lot of talking points. I know that there are a lot of sharp individuals in this room. I know quite a few of you already. So basically what I want to do is I want to have a very open and very solid and constructive conversation about energy systems in my building as well as your buildings, and energy systems that we've used in the past, what we're using now in the present, and then what needs to be used in the future. This is in regards to, personally, my building for Transamerica. As far as a discussion for when I talk about energy savings and energy systems for Transamerica in the future, I'm looking at 20 to 30 years down the road, because the systems that we choose today are going to be able to last 20, 30 years, 40 years down the road with proper maintenance and operational ranges. So chief engineers, operators of facilities, we make decisions that are generational. So if we make a good decision, but we could have made a better decision, that delta is huge. So I believe it's inherent upon us that not only look at our buildings like on an annual year, look ahead, but we'll look at it as lifetime decisions. So you want to shape your buildings, and you want to stage your building to where you don't paint it in a corner per se. And you're going to see some examples of that at what happened in the past in Transamerica, to where you don't paint it in a corner, to where you could look at staging ability to where you don't know of new technology coming out, but think of the technology that came out, 10 years ago, 20 years ago to now, So that's something that, I always keep in mind when I'm looking at and talk with my ownership to develop budgets and to do progressive budgeting, is that if I want to look at 6, 7, 8-figure projects, which we do, that in 10 years, that project still has merit. And then we'll talk about that, more in the future here. Just a little bit about me. I'm just a guy that knows how to fix stuff, and that's all I was, right? I graduated from the University of San Quentin. I have no formal, education. The cool thing about a building operator is that it's binary, right? I mean, I remember coming into the field and it was like, well, this guy didn't fix it, but then I fixed it. And then I just kept fixing stuff and fixing stuff and fixing stuff. I don't know how many times I looked at something, so I asked the person operating, what's this supposed to do? And then you're in charge of fixing it, and then you fix it. So that's where I come from on my background, along with the formality, right? I've been in the union now for 26 years. Started out as non-union, went into the apprenticeship, and did various certificates and programs of completion, facilities management at Cal State Hayward, when it was Cal State Hayward, Laney Junior College program, occupational safety programs, heating and air conditioning programs, in San Jose all the way up to San Francisco. So, and then that's it. And then I've been at the chief engineer for the Pyramid Center, 2008 to present. And then anytime, stop me if you got a question or anything. We're not getting into anything technical right now, but it's very informal, so just go ahead and step up and ask. A little bit about the building. So the building is a Transamerica Pyramid. Everyone knows that, but it's owned by Aegon Insurance Group. Aegon Insurance bought Transamerica back in, I believe, in 1997, 98. If you look at the building, it's on a Montgomery block that Clay Street, Washington, and Sampson Street surround it. That block has a Redwood Park that's open to the public most days. Yeah, but it's owned by Aegon Insurance, and we have a 20-story building and then a small little 9-story building on that. So that's our portfolio. So Transamerica, though, is just a typical Class 1A high-rise right now. Central chilled water and heating plant, 3 floors of mechanical systems. Those are just air handling floors. Domestic water pumping stations, that type of infrastructure. The HVAC does have 100% air economizer systems, which you wouldn't think so, because if you look at the pyramid, you really don't see the air inlets. But if you look on the west and then the south side, you'll see on the 5th floor, 19th floor, and then the top, which is a spire system, that's all of our air intakes. So it's pretty neat on how the architectural design was. They hit all the air inlets on that. The building did have utility steam for HVAC heating and domestic hot water up until 2009. We'll talk more about that. That's when Cogen really came online. The Achilles heel is the 24/7, 365 chill water operations. And that operation maintains chilled water at 42 degrees, and we'll get into more about that. But that's a real bummer on the building right now. That's something to where when I talk about, don't put a building into a corner just because you're making a upgrade, in the short term. Look at it more long term. Fully DDC Siemens Apogee system. They're also the life safety system, and then the building lighting control system, for better or for worse. So just a little something so now I'm talking a little bit more in the past for the energy systems and the infrastructure at Transamerica. Transamerica, it is a pretty complex operational building, and it's kind of hard to go ahead and jump into energy projects when I'm not allowing you guys to understand on where the building is at right now and the demands on that building, and then the infrastructure we have within that building. So hopefully I'm going to press upon and do a good job of getting you guys educated a little bit on the where it's at right now, touch a little bit on the past just right now, and then move forward as far as what I could do and what I'm doing in the future. It has 3 500-ton centrifugal chillers 2 years ago with frequency drives. Again, this supported the 24/7 chilled water operations. The chilled water system, again, has condenser water pumps, 100 horsepower condenser water pumps. Across the line, no frequency drives on the condenser water pumps. Frequency drives are on the tower fans. It has secondary and primary. I got a primary loop that's only 3 stories tall, from one mechanical floor to another, and then I have a secondary loop that goes from the 1st floor all the way up to the 49th floor. That's about 650 feet. So then we have approximately about 315 PSI head down on the bottom floors. Just a short little, so this is also best practices. So then I'm not going to do a slide for best practices, but just something that I do now, and I'll try to interject and for best practices measures, is that frequency drives, those are great. They're invented, they're awesome. They're just one of the best inventions in our field that's been around, or it started in the last 20, 25 years. But they're like TVs. They've gotten so cheap and so good, right? So remember frequency drives, where you put it on a critical motor, you'll have a bypass, and that'll just, if the drive crapped out, you bypass one across the line. Now I just buy 2 drives for a motor. The bypass, if you do the bypass option, you look into it, it's cheaper or at the same price just to go ahead and get a secondary frequency drive and then put it in one enclosure and then have just an A/B switch. So the majority of the induction motors that have frequency drives at Transamerica now have 2 drives and no bypasses. Also, too, is that what I learned as far as head pressure and being a high-rise building. Tim is at 345 cal, so he understands this, but high pressures. The tallest building I had was, 38 stories, but didn't have a chill water riser on it, right? So what happened is that when I went ahead and changed motors out for an upgrade I did recently for my primary systems and the frequency drives, I needed to upgrade my drive from a normal drive to a drive that would be put on like a conveyor for like concrete, you know, mining, that type of stuff. Just because the head pressure sitting on that shaft was so hard to do on a torque on the startup that the first drive I put in there wouldn't even turn. You know, so that's something, again, a lessons learned. Again, I didn't know just because I haven't dealt with pressures that high before as far as frequency drives. Cooling towers. That's on the, there's 3 garage levels. That's on the 2nd garage level. We have no roof, right? So most cooling towers are on the roof. So our cooling towers are inside the sidewalk on Clay Street. So to go back, what we do is that, well, let's do this. Don't mean to get everyone dizzy. But right on this hatch, I had one of these things here. Right on, my fan line is right there, meaning I'm drawing in air 2 floors below and through my inbound and outbound ramps, and the gate is an open gate, and so I'm sucking in air, and I'm sucking in air constantly because, again, I'm chilled water 24/7, so I always got cooling tower fans drawing in air into the garage, right? So that's very important, right? I mean, that's an inherent quote-unquote problem or situation for Transamerica. Always drawn in San Francisco air, i.e. 55 degrees, 65 degrees. I think people kind of understand where I'm going with this. Like, you could use that as an economizer, right? Drawn in through the cooling towers and then shooting out. I got 2 things in my hand. Shooting out to the atmosphere. So just the last part of the heat rejection. So that's the cooling tower fans. So just know that, again, just you need to understand the operational of the building before we move forward. Now, why the chill water, you know, the good, the bad, and the really ugly? What drives the chilled water? So what drove the chill water is back in the mid-90s, Nations Bank. Montgomery Security started up. I forget the guy's name. Went ahead and started day trading activities at Transamerica. That back in using early technology servers driving those operations pushed out a lot of heat. So we have an inherent problem, I believe, still to this day, and I'm changing it at Transamerica, and I'll get into that more a little later, is that we allow, as far as not so much building operators, but it's normal to where we have server rooms such as all this heat load being drawn up to a place, let's say 200 feet high in the center of the building. But then we have to reject that heat. And then so how do we reject that heat? We do it through infrastructure, you know, some type of means, whether it's heat rejection via air or via water systems, right? And it sounds silly right now. To me, it's seeing what's happening at Transamerica is just dumb. Why are we doing that? What happened was that back in the mid-90s, Montgomery Security sold to Bank of America. The guy, I forget his name, made millions and then took off. But what happened was that Bank of America came in and they literally gave the building in the low 200 millions worth of dollars to Transamerica to go ahead and set up their headquarters / infrastructure. So Bank of America had huge floor plates, around 20,000 square foot floor plates of trading activities. And they had, as the building goes up, exactly comes in, so the square footage drops. But then they had, you know, 5th floor was their server room. 6th floor was, you know, the trading activities. You know, 13th floor, 12th floor, between 7 and 8, they put in grand staircases. I mean, they just went ahead and just took over the whole building. They ate up maybe about 75% to 65% of the building at one time. Well, what they did is usually building operators will say, okay, tenant B of A coming in, what you're going to do is you're going to go ahead and you're going to build a separate system to support your supplemental needs, i.e. condenser water, tenant tower per se. So you go ahead and you put a tenant tower and it's a one entity, let's say, for this tenant. or the condenser water loop for the building in a whole. That condenser water then supports water source heat pumps per se that the tenant owns, okay? Well, that didn't work here because my condenser water system is pretty small compared to the building. It only goes two floors between the third mechanical to the first mechanical space on the ground floors. Condenser water only supports my central chilled water plant. My chilled water is the one that pumps up a chilled water riser, and then that's tapped off chilled water to a fan coil unit. Basically, it's like a radiator with this air blowing. So it takes the heat from inside the server rooms and then transfers that heat to the cooling coil, and then that goes through our chillers, condenser water, out the towers. So that worked back then. And what it was is that the Bank of America was told, okay, go ahead and, you know, engineer in a separate design, a separate, you know, cooling systems for your needs. Couldn't be done. They didn't have the resources, meaning the resources as far as square footage and as far as electrical infrastructure to drive that. So they tapped off, and then bam, we were married. The Transamerica was married to chilled water 24/7 through any supplemental loads that we allow up the building. So I think you guys know what I'm getting at is that what happened is that now those things can't shut off, right? Any operator here in this room goes ahead and says, well, we know that damn thing's going to crash, you know, on Christmas, you know, at 2 o'clock in the morning, because it's gonna, right? But it can't shut off. So what they did is that they're in the mid-90s, blah, 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 trading activities. These guys started with loads that are in a range of 175 to 225 tons of supplemental cooling. That's when the building was shut off. So what they did, the Bank of America says, okay, well, Transamerica, i.e. Aegon, it was even before Aegon, previous owners, is that you're going to go ahead and we're going to give you so much infrastructure, meaning that we're going to double your pumps, right? We're going to bring in all those brand new chillers that were new back in '98, and then they upgraded the pump sizes for the chilled water systems, and then they put in redundancy and redundancy. In fact, they put in their own 1 meg generator that's totally separate to back up their support, meaning that if the whole building went dead off the grid, Bank of America, could fire everything up, run their servers, trade, use the bathroom, use a toaster, use whatever. It was a very impressive infrastructure. It really was. But that's to where I could go ahead and people could come to me and go, look, at that time, it was a very lucrative deal as far as all this infrastructure for the building and income for the ownership, so who's going to turn that down? Or you could be on my side, well, not my side, I kind of think what I'm thinking is that, you know, as a chief operator, at that time, knowing me, I would have rose my hand up and said, okay, how long is this lease, right? There are restoration clauses that you could do, right, for deals like this. But then those weren't enacted and put in a manner such a way to where it got rid of the demands of the building, and it didn't. So here we are later is that, I forgot where I was going with that, is that it got put in a corner. The building got put in a corner to go ahead and keep the operations going the way it is right now. You can't shut it off. So we'll talk about it later. That's where I'm going as far as future work, that what needs to be done to go ahead and combat higher utility costs, to go ahead and lower my benchmarks, to go ahead and meet energy requirements in the future. All supplemental cooling equipment was engineered and designed for 42 degrees. Those are 5-ton units inside of a space on the 6th floor. They're redundant units. And what we talk about is supplemental cooling design 42 degrees, meaning is that if I know as an engineer, you know, a real engineer, a stamped mechanical engineer, is that if I know I'm going to get 42 degrees, I'm going to size my piping in a certain way. I'm going to how many cores of the coil I'm going to implement into that piece of equipment, what size chill water valve, supply valve I'm going to use to go ahead and provide 42 degrees. So now, if I'm at 42 degrees, and now I can't get away from having chill water reset. That's an energy saving program. Because I could go ahead and I could reset because my supply air to humans, I could reset up and then save energy, but then I can't do it to the machines right now. So there's another example of how I, as a chief engineer, am constricted because of past decisions within that building. Again, the good was, you know, the investment firms, they did put a lot of great pieces of equipment. They didn't skimp, right? I mean, those chillers are just outstanding chillers. You know, the pumps they put in are just outstanding pumps. Frequency drives, redundancy on electrical. Good stuff, good stuff. The bad is that this is where we're going into more as far as transitional away from a lease. Again, I'm always going to say, okay, get into a building when we talk about infrastructure or generational. They're going to outlast you or I, and then they're certainly going to outlast a lease. You know, especially in today's market in San Francisco. So what happened is that the bank took up, let's just say about 15 floors of the pyramid. Well, man, at those floors into different durations of time for leases. So basically, they gave floors up. So here we have a floor that's 15,000 square feet. That's on the 30th floor. That has great views. You know, the views there are outstanding. I will say that. That go ahead and you here, and then they go ahead and make a deal with another investment firms because the majority of the tenants in Transamerica are investment type mutual fund managers. They like that just because the security is paramount at Transamerica for obvious reasons. So if a money marketer, hedge fund manager goes ahead and has a bad year and they're dealing with our pensions, they don't just want anyone because that guy might want to talk to you, right? So the building really goes ahead and caters to those type of firms on the smaller scale than what was done for Bank of America. They don't want to, they being management are not going after those type of tenants anymore because they're seeing the after effects. So what happened is that new person that came in on the 30th floor, they had a tap off of chilled water. What they did is that they have, I don't know, 36,000 BTUs per hour, so they need a little 3-ton unit, 3.5-ton unit, and then they pop it in there. And then now they're going. And then we push back a charge for that. We put in a BTU meter and charge them back. Well, everything's cool, right? Well, no, because now what happens is that guy just went ahead and signed a 10-year lease. Now what do I have to do to keep, I got to keep the building on for another 10 more years, right? I mean, we go on vacations, we take holidays. My chilled water's gone, right? And I still got that little thing over my head saying, man, when that phone call rings and I see Transamerica comes up, it's like, oh, man, now what happened? And we're talking about servers that the equipment themselves are in the 6 figures, but the losses, right, depending on marketing, is in the millions of dollars per minute on trading. You know, when that market was hitting 8,000 on the Dow back in 09, 10, people were pissed all the time, walking, bad moods. Now imagine if their systems crashed at that time. You know, it's a different environment than, you know, it's bad enough having like lawyers in your building, but try having that in your building, right? Nothing against lawyers. So that's part of the, gosh darn it, on hand. That's part of the bad. Now the really bad is when B of A took out, they took 90% of the supplemental cooling load. So that 175, 225 now went down to 60. You know, I don't know if that's right math, but somewhere around there. 60, 50 tons. So now all that infrastructure that I showed before, the big chilled water systems and the big condenser water power pumps, those have to stay on for kidding me? And then everything was engineered at 42 degrees. So now I got, you know, a 500-ton machine trying to operate down at 10%. No, it doesn't do that. So I brought in new equipment you'll see that here in a little bit. But what happened was when that load was starting to go away, I mean, I'd go into meetings, okay, this floor is being turned back over in 2 months. Well, then what I'm doing is I'm putting false loads on the building, on the chilled water systems, right? I'm jacking my condenser water high. I'm closing down on my CFM going in my condenser barrel. I'm creating a false head on the chiller so it doesn't go off on low refrigerant temp. Because I don't want to go on low refrigerant temp at Christmas because I want to be with my family, which is kind of amazing, right? So then, but the one thing is it's cold outside. So now I go ahead and I got the water temp to drop while I'm trying to keep it up. Okay, well, all this steamrolled, right? From a decision to go ahead and go chilled water, then go ahead and give it the floors, and then go ahead and inherit the same system. While it needs a stop, and that's later what we'll talk about. We'll get back to this page later on. So I kind of scripted some stuff, but I'm just mostly ad-libbing like you can't tell. Oh, by the way, we have single pane windows. All those, quarter-inch glass. Insulation properties of a window's U value, right? 0 U value. So it's an interesting experiment because we know when the sun comes out and there's no wind, to when the sun comes out and there is wind and washing the windows. You know, our tonnage goes up and down when you kind of know that. And then when it's kind of cool, when it's cloudy and then it's sun and then cloudy, you see the equipment ramp up and down. And the solar intensity on the windows is around, we measure with a temp gun 110 degrees at times. And then you have a tenant that's, you know, maybe 3 feet away from that glass. Yeah. Yeah, it's film and shades and stuff, it's just too much. Then also it's a single pane windows, 0 U value. The precast is mounted on to structural steel, right? No insulation. So it's 4 inches of concrete and then just mount it to it and no insulation. So we have a fault ceiling up here, right? Let's pretend that this is my building. I have 3 feet of return air. That 3 feet of return air, then it's conditioned, right? We spent money to condition it. It goes back to my systems. I either get rid of it or reuse it, you know, and through my economizer system. Well, that's going through the skin of the building. Well, that's touching the surface of that cold concrete or that warm concrete, right? So that's another thing to where you fight on it. Because back in 72, you know, energy was what? 2 cents, right? So that doesn't play no more. As PG wants to go back to 2 cents, you know, then I could just stop talking. We could just go. So just a little sidebar. Oh, and by the way, I remember everyone. So those windows operate. They open. They center pivot, and that's how you clean it from the inside. A little side thing. Which, again, is a pain on the you-know-what, just because there's gaskets. So 3,678, I think that's it. I can't remember. Those gaskets start ripping, and then what happens is that rain starts happening with wind, and I start getting water being pushed in. Or whistling, right? You know, someone's trying to concentrate or do whatever, and then all you hear is this whistling going on. So then we know it's a gasket problem. None, thank God. Yeah, especially when the market was down. I'm sure a couple of them wanted to. But when, you know, if you're gonna call it on this building, you don't want to do it just because you jump them right there. You're going to be scraping right around there. You'll probably be changing your mind right around there, and then you'll be unconscious right there. So, yeah. Oh, and then by the way, too, so these wings, I know I'm ad-libbing here, but hopefully you guys find it interesting. One of them is the smoke shaft on the east side, the little gull wings. And then the other, on the one on the east side is the elevator shaft from the 27th floor up to the 48th. On the 27th floor, it starts somewhere right around here. Then if you made these elevators in the middle, you're going up through the middle of the floor of a 2,100 square foot floor, so then you can rent it out. So then that's why they incorporated the gull wings for the elevator shaft. On the other side, it's a smoke shaft. It starts in the middle of the building and then ends up coming out of the shaft because it's straight up, but the building tapers in. All right. All right, so we're on the cogen plant. So what I want to do is I want to kind of deviate from the script here because I wrote some notes and I want to make sure I don't skip anything. And I wanted to talk just a little bit about building management and chief engineers and building management as far as property management companies and ownership. So chief engineers, back in the day, and I'm stereotyping, in the early 80s, they were the ex-security guard that had the big thing of keys and they knew where all the closets were, and then they graduated up to be a chief engineer, you know. Then I think what's happening is that, and at one time, I believe chief engineers were property managers together. I know Jose Gomez, the predecessor for my building, was the property manager and chief engineer for all the Embarcaderos in the 80s, early 80s. So what I wanted to point out is that chief engineers and property managers, GMs, and ownership, they all have to be on the same page and cooperate. Now, there's people in this room that know that, man, my GM and I, we go at it. We go at it pretty good at times. But the one thing is that, you know, it's like a marriage that you just can't get out of. You know, you got to go ahead and make it work and have the mutual understanding and respect with each other that, hey, it's for one common goal. Now, his common goal or their common goal might be for the bottom line of a spreadsheet or instructions from their ownership. While as the chief engineer says, hey, I got a good project, why are you saying no to me? Because I'm making it for the betterment of the building, you know, not just because of my ego or I want to do this or I got a little cut in it or something. No. So what I've learned in my career, and I've seen it to where a chief engineer, a property manager, sometimes they'll just be oil and water and they never talk to each other. And that I believe that can't be the norm. I think what has to happen is that you have to go ahead and somehow between the GM and the PMs, property managers, and the chief engineers to go ahead and find a mutual understanding and then a common goal, right, to go ahead and present as one to ownership, meaning that my GM will go ahead and listen to this spiel, right, and then what he has to do is not only I have to go ahead and educate him, right, because he doesn't know all this technical stuff, quote unquote, but then he has to go ahead and then buy into it. And then they have to go ahead and then sell it to ownership. But then they have to inform me, look, we can't do this at this time, or we don't have the resources to do it, or I just need more information, or, you know what, I just don't believe in you yet or your project yet, you know. So then I have to use my talents to go ahead and find that common ground. So I think, you know, as I talk to a lot of my cohorts, with, you know, Tim Danz is in here right now, and then the younger chief with Windsor, you know, is that I believe it's a better evolution. That's what's happening in my 26 years. I've seen chief engineers just totally complain about their PMs, and believe me, I complain about my PMs, but then but they'll complain about it in the past and then never come to resolutions, and the building stands still, right? As to where, at least to myself, I can look anyone in the eyes because I don't get along with my property management at times, but look at the stuff that we have done in the past 8-9 years, and I think that's the goal. So that's just like me being on a soapbox here and doing it. So you know, kind of the key, and anyone online, I think that's paramount, that you have to have that type of you know, common goal.
Somebody's knocked on your door, you've knocked on somebody else's door. Look at changing that.
Oh yes, no, we have.
What? The Transamerica building is not about to be torn down.
Right.
Probably ever.
Right.
What's the long-term outlook? Because obviously it's a hugely expensive job.
Yeah.
But what would be the long-term?
As long as it's not in movies, because in movies it always gets torn down. So, but oh, go ahead. Oh, the question was about the question was about the windows as far as what the long-term view of that project is, or that type of job coming up. the long-term view is what it does is that they prioritize, again, to answer your question, is that my management looks at, and this is kind of we, as far as internal management with myself, to our ownership, impress it upon our ownership that they're long-term. Aegon is, the owners of the building. Some owners buy small buildings, wait for the market to come up and flip it, and they don't put nothing in it, just like a house, you know. But that's not the case for Transamerica, which is a good thing. So the long-term view is that we impress upon our ownership that we're going to put together a 10, 15, and 20-year plan, and this is what we'll talk about here in a little bit. So we, as far as management and on-site management and chief engineer, along with the construction manager, looked at installing a window washing rig on top of the building. Go back real quick. So on top of this building, right at the top window line is the 48th floor. On top of the building is the 49th floor, and then on top of that is the 50th floor, which is the spire. And you'll see a picture of that later. And then there's a platform there. So you could put a window washing rig. These louvers, these are air louvers right here, and that's where you can see it, you know, lighting glow, and you'll see that a little bit here, is that your door on all four sides. This window washing rig will be on a turret. And what will happen is that this door will, we engineered this, we spent quite a bit of money, I'll say in between $300,000 to $450,000 in engineering that we have on hand, is to go ahead and pop the doors out, they roll up, and then a telescoping rig comes out and then goes ahead and drops. So it's, sorry for the people online, you can't see me, but if the building's angled and you pop out, right, the harness, the cab stays close to the building, but then as it goes away, the arm has to extend to support. So you never remove yourself from the building. That is a long-term goal accompanied with replacement of all the windows. So replacement of all the windows, we have a budgeted cost anywhere between $8 to $9 million. Those will, what I suggested, and I got a little bit of pushback, but then we, you know, just because of the operational point, I suggested, and this is the way we budget, is for sealed windows, triple pane windows. There are two panes with a film in the middle that kind of quote unquote makes it lighter, obviously, but then makes that triple pane insulation. So I think the U value, don't quote me if I can remember right, went up to a 9. And then PG&E did come out with engineers and measured a possible ROI, which is, well, I'll be dead by then. But there was a KW savings. Now, what happens is that in my niece Victoria here, she's a property manager at 60 Spear. Property managers, and Tim and anyone could kind of correct me if I'm wrong, what happens is that you would look at big projects like that, and I've learned this from being here and learning underneath the gentleman named Phil Rappaport, is that you go ahead and you talk to ownership, and then you stage projects, and you keep up with the market, and you keep up with your leasing people, and you say, okay, we project that the building is going to be this occupied on such and such a time, whether if it's 6 months from now or whether if it's 2 years from now or whatever. And then you go ahead and you possibly look at progressive budgeting. Then what happens is that you look at leases and how leases are written. Then you look at projects that could possibly save KW, i.e. capital improvement. Then you look at leases to where if that's something that project can be amortized back to a certain percentage to the tenants that are occupied at that time. Meaning that if I have, and I just signed up big leases, and for 10-year leases, then it's possible that I could go and amortize those dollars, that project back for that capital improvement project. So that's a little something to where I've learned to where, you know, Arthur asked that question, what's long term? You look at those big monies. Now what you need to do, again, more of my soapbox thing, is that the chief engineer and the GMs and the PMs have to go ahead and find and use their talents to find a way to find the funds for that. Because, you know, ownership, all they're going to do is that spreadsheet and see $9 million with no ROI. But it saves KW. Now will it go to capital improvement? Now can we do an amortizement back to the tenant? Now things are starting to roll, right? We've done that before, you know. And don't feel sorry for the tenants. They drive Mercedes and Range Rovers, and that whole garage is filled with them. Lamborghinis. Okay, so I digressed a little bit. So let's keep back in subject. Am I good on time? Yeah? Good. Okay, so now we're talking about recent past energy savings projects that the pyramid started with, and then I helped start with, and then complete it and operating. Back in the mid 2000s, a company called Northern Distributed Power came in San Francisco and did a small little handful of cogeneration plants. CHP, combined heat and power, some people call that. So cogeneration is exactly what it means. It means more than one. So basically what we're doing is we're bringing one measurable unit of energy, and in this case it's natural gas, and we're putting it into a prime mover, which is a reciprocating engine, and then we're turning a generator which transforms energy into moving electrons, i.e. electricity, right? 1 unit of natural gas coming in, 1 unit of measurable kW, right? Unit energy and energy unit. But then the byproduct, because of the BTUs and the natural gas, the BTUs, the friction within the so in BTUs of combustion, then go ahead and translate to where that prime mover engine gets heated, needs to be cooled just like our car engines with your radiator, but unlike a radiator, you just go ahead and extract that out through the atmosphere. We go ahead and capture it in water. So that's called our jacket water system, because it's a jacket water system because the engine block has channels within it called a jacket, and then the water goes in there and then takes off. So then, thank you for the questions. So then what happens is that now we have a unit of energy. There's my cogeneration. Gas coming in, and I got to, right? So there. Go back to where Northern went ahead and did some cogen plants throughout the building. Excuse me. They went under a financial model of looking at leasing the space, building and installing the cogen system and operating it, producing electricity with the hot water byproduct at a small kW charge, back charging it to the owner of the building, and then the owner could go ahead and charge a lower rate to the tenants, right? And then everyone wins. Everybody just basically saves of shaving, let's say, a couple cents off kW. And for the life of and for no down payment from the ownership, of course, you're going to look at doing that. Well, what happened is that, again, this is to where stuff on paper goes ahead and meets reality, right? Engineers that go ahead and design, real stamp engineers, PE guys, that go ahead and put a project on paper, and then you go ahead and build it and turn on the on switch, come on. That's the where guys such as myself, Tim, and Windsor comes in, and then I think you back there is that, no, now we have to deal with that engineer and we have to fix it, right? So that's what happened, is that when they started, they didn't have that infrastructure to keep those units running. So if you're not running, right, your cogen, if you're not producing kW hours, your financial model just went to hell. They went out of business. Transamerica's cogen was the last one that they built, but the best thing about it is that they sold it to us. Transamerica didn't want to do that lease. They bought the equipment. So when I came in June of 2008, it was supposed to be up and running in 2007. The feasibility study was horrible. It didn't work. It was incorrect, page after page after page. So it's kind of no wonder that company went out of business. But then when I got there, it was pretty much physically 95% completed. We had a little bit more, and then I came, as my little bio said, it was from being a day operator for a cogen plant for Chevron in Concord. It's been recently dismantled 2-3 years ago now. That was a 3 meg plant. But the same type of concept, engines the same, generators, right, pumps, piping, what they did with the byproduct was all the same. So I kind of walked into this, but then it's like, hey, I kind of know. I hired on, and I didn't see the cogen plant. They just said, hey, it was down. I go, well, we'll fix it. That's kind of what we did. So let me go ahead and explain and give some more outline here. So this is the graphical page, and I hope everyone can see the numbers a little bit. And then what I'm going to do with my little pointer is that I'll outline the cycle of the chilled water, how the jack water pipes out, and then what the apparatus is that uses the byproduct. Again, we're 24/7 chill water, right? So we have connected loads that are big chillers, big pumps constantly on. So this is, and then, excuse me, let me back up. We have 2 gen set units, so generator sets. And then each one is 500 kW. Each one is connected to a switchboard A and a switchboard B that are not in sync with each other, but generator with switchboard 1, which is in sync with utility, generator 2, switchboard B, which is in sync with utility. Natural gas comes into the engine, drives the generator, pushes out. At this snapshot, it was 350 kW worth of power. That's it. That's generator. Big deal, right? But then the output temperature is on the water side. So we go ahead and take water coming out of the engine block, and it's 270 degrees. I'm going to use this one here. 210 degrees, right? Output, and that's sensible heat. That's, 210 degrees, you touch it, hey, that's 210 degrees. Then what happens, it goes through a heat recovery unit. Then it comes out at, 4 degrees higher per se. Sensible on the water side. Well, this heat recovery unit is a tube bundle, but what goes over that tube bundle is the exhaust air of the engines. The exhaust air coming out of the engines is almost 1,200 degrees coming out of the cylinders, right? So then that heat, that sensible heat, but it's in a vapor. It's air temp, not water temp, right? It's not a totally saturated element. Then it comes out of that heat recovery 400 degrees. So, quote unquote, it's given up water. So the latent heat ratio is not 1-to-1, right? It's way off. It's way down. It takes a lot of heat from the air to go ahead and raise 1 degree sensible in a saturated element like water, 1 degree. So we'll give up 1,200 degrees of air temp, and then to go ahead and get 5 more degrees, 4 more degrees per se of temperature in water. That's critical because my target for the cogen jack water is anywhere between 210 to 215. I need that. I can't do anything else less than that. Then I get reduced. That 210 is the energy source for an absorber chiller. That's key, right? Because I need chilled water 24/7. So if I didn't have this absorber chiller, I had an electric chiller on. And I had an electric chiller on that was a 500-ton unit. That horsepower on there is 399 horses, right? You're not using it all the time. But these guys, this one, I think it's like 2.5 horsepower pumps just to mix the solution around to get tonnage. This is a 300-ton unit. Water goes in, helps with the chilled water, comes back out, goes through TCV valves. It sends the piping system, jack water system, goes through a plate and frame heat exchanger. That's my building heating hot water. That's comfort heat. So what that does is that supplies heating reheat coils on my perimeters. That's pretty common in San Francisco and other parts, I'm sure. Then whatever left over goes through domestic hot water. That's just a little shell and tube. Office buildings, they don't have a lot of hot water demands, right? It's just bathroom sinks, and that's it. If a tenant has like major dishwashers, you put in like little spot heaters and such and such. Then what happens, this is a plate and frame heat exchanger. If I have too much heat going back to the engines, I dump it through cooling towers, but I'd really ever do that because if I am doing that, I'm setting something up wrong, meaning as an operator. I use so much energy to get this heat, and now I'm dumping it out of cooling towers. That's something to where, again, something's wrong happening as far as operational wise. Then I send the jacket water back. So now it's at, what is it at? 150 degrees, right? Now I'm sending it back to the engines. But my engine's delta rise is 20 to 22 degrees, and that's it, right? So what happens is that there's a TCV valve, a three-way valve, to where jacket water coming out of the engines, all that energy I put to make that warm, make it hot, now I got to send it right back in short cycle. So I got to mix my 150 and make it 196. That's my target going into my engine block. So then at the very end of it, through everything, I'm getting 210, 215. So that's a bad design. It's a flaw in the design. Am I smart enough to not design it that way? Probably not. Not back in the day, you know, not back when this thing was on paper. But what happens is that here's a good idea, but it wasn't the best idea and the concept wasn't the best. And then how much out of this, these guys are going to last. I've got over 33,000, doesn't show on this, but over 33,000 kilowatt hours on this, right? No, 33,000 hours, I should say, not kilowatt hours. And on this one too. But I'm choking back. I'm sending back 45% of the water in volume that's coming out of my engine block right back in it. Something's wrong there. So what could have been designed different? Could this jacket water system been designed in enough volume, piping size enough to where it goes through a short cycle of piping infrastructure locally and then through one big long heat exchanger and just take it to where it could go ahead and just transfer that heat? And I'm flowing 100%, right? I'm out of here. I'm into this long heat exchanger. I'm right back into it full bore instead of being choked. So that's what I'm saying is that it's not scary, but it kind of is scary is that engineers such as ourselves is that, you know, we can make these type of decisions, maybe not this one, but we can make decisions for the building and ownership and by and sold it to our GMs and our owners to go ahead and go with our design, to go with my design coming up here in the future. Is that the right one? You know, that's to where, you know what, you bet it. You bet it out. You go ahead and I get called to talk in this room, there might be someone who goes, hey, Doug, that's a bunch of BS. That ain't going to work. I want to really talk to that person, right? I went ahead and when I started this Cogen up, I didn't know exactly how to operate or what it was going to do, but I showed the end result, and then you guys will see that here in a little bit, is that I invited mechanical engineers, 60 of them from the Golden Gate chapter of their engineering group, took them to lunch, bought them lunch, and then showed them this, and then, man, those guys rose their hands and said, no, 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 and then it was like, okay, you guys are coming back, and then they taught me, you know. So that's something to where, you know, one mistake, great concept, but just that one mistake and it's costing quite a bit. All right, I better move it up, so I'm going too much of a tangent. They're Untitled absorber chiller, drawing 17 amps. Let's go back. This is the one thing I got to really hit. Okay, so let's talk economics of this. I spoke about the operations and what I do with it. The economics of this is that we go ahead from commercial energy, in which Jens is not here. We're going to get that guy and terminate his contract. Jens, if you're online, your contract's done. We buy from third-party commercial energy. They're great, outstanding. I'm just joking. They're good company. They're based in there in Oakland, so there's a little plug. So we buy third-party from commercial energy, and then we get a transfer fee through PG&E, so many BTUs. So it's roughly around 4,000 PG&E charges us, and then we're hitting around maybe around 28 to 32,000 a month for gas, you know, depending on operational days and all that. What we did is that I attempted to good numbers, but I wasn't really sure, meaning that I need to see of these engines, these gensets. So they come with a name, but then efficiency to me in anything is just try to make it simple, because when I get into like heavy mathematics or energy formulas or engineering concepts, then I try to be more of a simpleton because then I can understand it, right? But gas coming in at a certain rate, and then you're producing whatever amount of kW, and then go ahead and then calculate out what that rate is as far as an energy efficiency, meaning cost going in, cost coming out. What's that kW cost comparative to PG&E coming in? So I couldn't really figure that out, so I hired a mechanical engineer through my company, Able Engineering, and he went ahead and developed the whole system of the cogen system energy efficiency. So gas coming in, I'm producing kW, but at what cost? PG&E is going ahead and they're charging me 15 cents, right? But then I'm producing, let's say, 5 cents. So now is it a savings back of 10 cents? Well, simpleton that is, but how much energy am I using from the generators on the normal day and what time of day? 70%. So now it's a weighted balance, a weighted average. So my blended average, let's say, is around 8 to 9 cents, right? Depending on, winter rates and summer rates, peak demand, blah, 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 but, try to keep it simple. So now what I could do is that I go ahead and I took the natural gas cost coming in, and I'm producing kW at 8 cents. How much is my hot water costing me? That produces energy for the absorber chiller, my building heating, and my building domestic water. How much is that costing me? Does anyone want to take a guess? 0. Free. That's the home run, right? The home run was the absorber chiller at, I'm getting better, at 17 amps for that low kW rate, right? And I'm getting a sorry guys. I'm getting a split. I'm getting a pretty decent split of 7 degrees, right? So I'm doing some good. At 17 amps, how many pennies is that per hour? Then I'm getting free hot water. Now, if I didn't have the hot water, what was I using before? District steam. So NRG, the president, when I went ahead and called them up and I said, okay, send a guy out in 3 days from now to lock up your valve because you guys are done. And then they go, what? You mean you got that thing running? Because we're paying them $40,000 to $60,000 a month. Now we're paying them nothing, right? May 1st of 2009, we paid them $16,000 for a standby. We didn't use any pounds, right? June, nothing, and it's been nothing ever since. Now here we go. So now I'm on a roll. Thank you. So I'm going to try to hurry and fly through this. So I made this spreadsheet. Took me a while. Spell check was a bitch. So this year 1 to year 2, 3. So basically, we wanted to find out what one our ROI is, and 2, what the cost avoidance of cogen for the lifespan of the cogen system. Okay, so May 1st, 2009 was the first day of operations. I generated this spreadsheet, I think, late June of 2010. So from year 2 on over is projected. It's not true anymore. It's within a ballpark, but it's something that you guys have to understand that June 10th, that's what I only had going, right? But these in bold are actual numbers. So this baseline model, the $2,025,000 and change, that was the invoices for utility prior to cogen 12 months before. May 1st, 2009, post-generator utilities, cogen utilities, 932. Ancillary costs, I developed that account number because anything that I paid for cogen, meaning a special wrench or sensors or anything else, if I didn't have cogen, I would have never bought those special wrenches or sensors. So you have to accumulate that cost. Then cogen service. So, I think I'm pretty good, but I'm not removing heads and rebuilding lower ends and, changing out heads and all that kind of stuff. I did. Our service contract is around that time or that much per year. Scheduled engine service, $0. So the first year, I just turned it on. I don't need to go ahead and rebuild engine. Then chiller 4, that's that absorber that uses the energy source from the cogen. That's a service contract. If we didn't have the cogen, we wouldn't have that cost. So you have to put it in. So these are actuals. These are canceled invoices, canceled checks, right? And then so there's no dispute. So post cogen cost. So the delta, the first year of savings was $885,101, and that you can't argue that. So that was my biggest thing, is to capture all the energy and all the costs, and then to see what the delta is, and that's what we came up with. Did I project that? No, but that's what it came out with. So, stuff like I think year 3, which was 2011 and all that, bad cogen operations, stuff broke down. So, man, I probably pushed off $400,000 into that. So it wasn't 1 million way down. So those are cost avoidance. So, and then you gotta, yeah. So that's it. But that was a pretty good spreadsheet. I was actually kind of proud of that one. 10 minutes. So because we kept it moving. It should be a living document, I think, until it's dead. And it's a simple payback, meaning, go give me 5% on, 800,000, right? But they didn't do that. So it was about 4.8 years. It paid off in, I believe, fall or beginning winter, maybe 3rd or 4th quarter of 14. So it's done. 10 minutes? Okay, so let's go ahead. I think I'm all right. Bad graph, I'm sorry. PG&E goes ahead and sends out a great electricity summary. I don't know, 11 pages long. Talks about KVARs and all that kind of stuff that I don't know anything about. But it looks cool. So what this is that this is usage history. So this is 666,000 kW, and then this is my consumption. Here's a little line, right? So here's January. This is 2015 was quote-unquote bad cogen operations. We had breakdowns. So at the beginning half, and it was at the half, it was January to July, you could see my consumption was up, right? This is consumption. This is peak demand. So I think everyone knows what peak demand is, right? Good. So my peak demand changes because I have a high baseline, which, why do I have a baseline? Because I'm 24/7 chilled water, I always got stuff on. But I offset that with peak demand with cogen operations, meaning if I'm producing on site 1 meg, I'm not taking a meg, right, from utility now. So if my building load is 1,500, and let's say it just stays that and it's a constant load and it's flat and it's consistent the whole way through, my peak demand is what, 1,500, right? Or excuse me, 500. So then now 500 times whatever rate, what, $18 per kW times $24 per kW. New York, it's much higher. So that's my peak demand charges. So what happens is that here I have consistency on consumption. When bad cogen, higher, I'm exporting in, what's that, 540 kW hours. Then I turn on cogen. Cogen has good months, last 6 months. But then I'm fluctuating. So what happens here, and I always use this story, a spider, a bug, crawled into the smoke detector in the cogen engine room, shorted it out, alarmed it, cogen matrix shuts down, bam, I'm importing in 1,000, right? That's just quote-unquote S happens, right? So that's what happens. So that's why cogen operation is so critical for this building. It could be for other buildings, obviously, when you have a high base load. So what happens is that now I go ahead and I show the effects of a bad cogen year, and the effects of a bad cogen year was 85,000 and change for peak demand. So that wasn't, quote unquote, any consumption or higher consumption. So if I go ahead and I could develop a project, let's say that costs 85,000, and then that project could go and consistently save, well, as a 1-year ROI. Well, you're not really going to find some projects out there. But let's go ahead and say I find a project and they go, hey, you got a 5-year for an ROI, right? Meaning that if you could go ahead and offset that, now I got a benchmark to go ahead and think of something and invent a project. And that's a cool thing, right? Now I've got money. Now I can show it. My management, I go, hey, this is how much it costs, and they they can't say yes fast enough because it has the ROI, because you could see this. There's merit, right? Past project efficiency. We're going to run through these real quick. 2010, 2011, we put in a fan wall infrastructure, hot water SSTO program, pony trim chiller install. Supply fans, 101,000 CFM fans, 2 of those, and the other one was 75,000 CFM. We replaced 2 of those with a fan wall system. This is kind of what it looks like. It's just a wall. It's kind of cool. It was made by Hunt Air, which is up there in Oregon. And then also is that we installed new cooling coils. This has my chilled water system. This is for building standard HVAC systems. And what that does is that pushes out air into a common riser, duct riser, and that taps off to the floors, so duct floors, because I had the hot water reheat. The cool thing about this is that all this was custom-made piping, and on this one it's copper coils. A year later, we did another bank of coils. Copper went up in prices. We did a dipping film. The heat exchange rate was really close, and we saved $32,000. And then that was over a couple beers with the vendor, and then he goes, hey, copper prices went up, but there's this dipping process that, you know, looks good. And you know, just networking, right, was $32,000. Hot water SSTO program. This thing was, I liked it. I liked the idea of it, and I'll kind of touch on it. Is start, stop, time optimization program for hot water systems. Basically, I got a heating hot water that goes for, again, comfort heat, and I wanted to put in, and thank God for spell check, because there's no way I came even close to that. Installed an algorithm. I thought of an algorithm into our Siemens Apogee system, and basically what you did is you look and trend at certain interior and exterior condition zones, meaning that outside temperature, maybe humidity. High-rise buildings are 2 buildings, right? Lower is calling for heat, upper is calling for cooling, so now I got 2 buildings. So you take the problem person area of heating that floor up, and then what you do is that the program will retain his trends, and then what it'll do is it'll learn. You know, it'll say, hey, I started the system up at this time with this cogen system's on and the backup boiler system's on, and I was hot water temperature at 160, but I should have started a half hour before. So then what you do is you start trending out and you see those certain conditions, and then see if the program starts a half hour before to go ahead and hit those marks of those critical loads. And it does. And then what happens is that it kind of gets erratic, and then it kind of gets smart, and then San Francisco climate is nice and common, bless you. And then basically it doesn't move, you know. It starts maybe 20 minutes here, and then it starts maybe 30 minutes there. And then how much of that is actual savings? You know, at first it's kind of cool. It could save a lot. I wouldn't really know how to quantify it. But since it doesn't vary so much, and then it depends. Sometimes we have a warm year. Sometimes we have a, so it's pretty much just to where you're not wasting heat, meaning I'm starting up too early, like 2 hours early, you know. So that's the backbone of it. Again, it sounds cool. It's a good thing to have, and it really didn't cost anything. It was just programming time and kind of some thought. All right, and then we put in a pony trim chiller. So what this is that, again, I had a 500-ton chiller. At now the low loads, because the banks went away, right? The main supplemental cooling loads went away. So then I'm down at 50 tons. Well, I was at 55 kW per ton for the prior chillers. These guys now are getting down to 3 kW per ton for the chiller. You know, you add a lot of hours to it, and then it'll pay back itself, and it's great. But again, the ROI is not there, because for one, a lot of times this guy's off during the day because I'm dealing with the absorber, and then two is that, well, two, ROI, not a lot of hours, and the infrastructure to put it in costs a lot, so that ruined the ROI. But then I needed it. So this guy could go ahead and go down to operate at 10 tons. It's a 180. It's a 160-ton unit, and it could go down to 10 tons and operate and be efficient. So that's why we needed it. But again, this was something, a $500,000 project, all said and done, that Now the building painted itself into a corner, went ahead and bought into Bank of America. They wanted chilled water. They signed that deal. They gave up floors. They kept the chilled water going, and that's where we're at right now. Now, that's a frictionless bearing. It's kind of cool. This coming year, so this is a lighting project. So there's a spire, and then what we're going to do is put in LEDs coming up, and then we're going to go ahead and upgrade these lights right here. So these are the old metal halide lights. We got 1,000 watts, 750 watts, and 400 watts, or 450 watt bulbs. It's about 82 kW per hour to go ahead and run. They only run 4 to 5 to 6 hours, depending on daylight savings. And it costs me $35,000 to $40,000 a year to operate. But to replace them, we're at $425,000 for replacing with LEDs. Even if they go ahead and save, to no cost, right, LEDs, the payback is way out there. So it's more of an infrastructure type, thing. But that's our projects covered for 2016. Working on that. All right. So how much time? 5 minutes? Give me 5 minutes, please. All right. Now, are you ready for 2013? Governor Brown signed the climate bill, right? I got a copy of that right here. Basically, what it wanted to say is that the state will also need to become twice as energy efficient by 2013 under the new law, right? The law now. For existing buildings, that can include newer appliances, improving heating and air conditioning. Well, no duh. So, but with chilled water 24/7 at Transamerica, am I ever going to be twice as efficient? Don't have a chance. So now I have to shut that chilled water plant, right? It's got to go. So now how do you do that? Well, what was the need for those chilled water plants, or that water supplemental cooling? With server rooms. They put them up high. They put them in my building. Get them on my building. Put them in a colo facility. Put them in, all this open rack, right? Air going in. Put that in my garage because my garage slots are open. And I could turn on some small horsepower fans, and I could draw air, and I could draw air in those. Now, what do I have going? Now I got all that horsepower, right? The pumps, the chillers, everything being driven right now, and it's engineered. I got a feasibility study right there. Nice corner. $40,000 we spent last year for the feasibility study, and we have a meeting more on it tomorrow. This project is budgeted for 2017 right now. So you have a cold pressurized deck. You see it's as tall as a guy. Fans go ahead and suck in outside, let's say garage air. Clean it, make it humidity, all that kind of stuff. Do what you need to do to filter it. And then, suck in that air. Then also go ahead and put in maybe a small chill water or DX system in there. And then the DX, go ahead and inject out down, let's say the next level garage. You're putting heating air, rejected heat in my garage. Who cares? It's going to dissipate. Or if it gets too hot, you can tie into my condenser water system. So we went ahead and this feasibility study calculated out, how much kW you're going to draw in for, mechanical cooling now. And the kW ton hour, and this is in cost, is 25 cents per ton hour. This newer systems will go ahead and reduce that down to 5 cents per ton hour. So an annual savings of excess of $190,000. So right now I have a cost. I'm trying to get it down right around $1 million to do, and that's infrastructure, the whole thing, not just these racks. Not any of this, because what's happened is that I have to build fiber now, right? Because if I don't allow the tenants to go ahead and put computers in there and go ahead and communicate, well, how are they going to communicate when they're down? And you got to push in fiber. So that's a $100,000 project right now. And that's built into that $1 million. This is, we're not going to get to that. We're not going to get to that either. So now, what happens? Oh, let's go back. So what happens is that I want to shut down the chill water systems. I want to go ahead and put in the server farm. And then this is more of a relationship now with the chief engineer and the general manager. And it took me 2 years to get to this point with my general manager and ownership to allow me to spend $40,000 on my idea with the feasibility study. This goes back to, again, harping on you have to have that relationship to go as one to the ownership, and then that's where we're at right now. I have to go ahead and have the ownership say that, look, this is our next move. We have to lower our baseline. We got a law in 2013, right? Everyone remember 9/11? That was 15 years ago. 2013 is 15 years from now. It's gonna blink, right? 2030. Yeah, sorry. So then, now is that I had a baseline here with Cogen. I lowered it. Now turning off all those chillers, I lowered it more. Then what happens is now I'll go ahead and I'll bring in maybe tower-free cooling right here, or a pony chiller, and see what the cost per day for my human needs are for cooling. Then maybe I look into batteries, stored batteries, because I got a Cogen that operates at a lower rate. Maybe I go and turn that on and pop in and charge these batteries up, and then go ahead and pop these guys on during peak demand. And peak demand goes ahead and accounts for, this is to where our demand charges in 2000 kW we did, 25. And then when Cogen came on, we went down to 17, and we went down to 269. But then we'll go ahead and stay down low, but PG&E is, the rates are still going up for peak demand. So no matter what, my KW goes down, my rates go up, we're going to end up going right back to where we started from. So we got to get off that grid, right, especially during peak demand. So that's what the batteries are for. So the batteries are not energy efficient, they're cost efficient, because there's still KW being used. All right, we're almost done. Now, my ultimate goal is to go ahead. Now what I do is I have a family of energy savings projects where I started from and where I'm at right now and what I want to think of it being in the future. Now I want a building automation system, put in a big screen TV here. This is that's cable, obviously it has cable. That has building automation, Cogen operation, and more building automation systems. All that talks to one. And then what happens is that basically what we do is we get to a point to where this is a page off my Cogen system, and on this gen set, this has natural energy going in, energy that's being recovered, energy in my Jackawater system, energy that's being used, and whatever is wasted. That's an efficiency for that engine by itself right there. So why can't I have that for the whole building? Here's my whole building system. Here's my chiller systems. I want an efficiency number right there. I'm 80%, I'm 85%. Then I got my boiler page. I want the same thing for that. Then I got my fan page on the 5th floor. I want the same thing for that. And then on this big screen, I want to see what the building energy efficiency is. Energy being used, energy coming in, and energy being wasted. You can get an efficiency. We know what the PG&E rate is, so do it at real time, and then go ahead, and if I'm coming in and I should be at 70%, but I'm down at 65%, where am I at 65%? What's drawing me down? So forget about now retro commissioning, ASHRAE 2 surveys, everything else. It's just constant, real time. That's what I'm tasking my building automations to do. So then, here I go, big drop the mic type thing. So you let the systems decide. You let the cooling system to know what run, what's the rate per ton, what systems is more efficient. Make it so the dumbest thing about the daily building operation is the chief engineer, me. That's it, right? Because I don't know what's happening out in the field, what's being now, my boiler system's dropping out to efficiency right now. I don't know. Maybe it's tunning or short cycling or something. But that's why you need a system, an operating system, I believe, to go ahead and say, hey, this is happening automatically. You guys go now go do something about it, because humans aren't going to catch it. So, that's it. Sorry. I thought I wasn't going to make it 45 minutes. I know, I go on and on. Any questions? Just, Tim, how you like your building? So we did dimmer colored. So I got cards up here. I've got cards up here. And then the Pyramid Center, this website's pretty cool because it has, like, you know, stories like Eye on the Bay, Pass Eye on the Bay, and some other news clippings and movies that the building's been in where you can see it collapsing and all that. I like that. So, all right. Sure.
You're getting efficiency on your absorber chiller if you increase flow through your genset. That's the driving factor. Not short cycling your jacket water.
As far as the question was, is to go ahead and then gain efficiency for my absorber chiller if I do not short cycle for my gensets. I don't have that option.
I know. Background trying to flow through that. You're saying that was the inherent design flow?
The inherent design flow is non-avoidable, meaning that I have to have a certain amount of GPMs going through that jack water. It's a fixed GPM. And then I have to have a certain amount of temperature that goes into that engine. So the GPMs coming out is fixed, it's constant, and the temperature has to be maintain a constant set point. The generators coming out and through the systems itself as it goes past the heat recovery unit is targeted at 210, 215, so I can do any work. By the time the temperature comes back, I'm around 240. So then now I can't push, 140. I can't push that 140 back into my generator because I'm only going to get 262 out of it, or 162 out of it. Thank you. So to answer the question, I have no way of avoiding this. Or it was a design flaw right when the ink went on the paper. Yeah. The engine output is only rated at 506 million BTUs an hour, right? So that's enough to go ahead and get a 22 degrees or 20 degrees delta rise. So the inherent regular piping design and how it was used and pipe and the runs and all that caused it so there was so much delta T loss on that output that you needed to go ahead and push back in. So it's not so much cooling the engines, it's a matter of making the engines set up so they could hit the target of 210, 215. And then that's something to where you guys, feasibility study comes into play, a team of engineers that have cogen experience, and along with day operators, guys like myself and other guys that I've worked with in the past. That's where you get on paper and then you start talking about it. It shouldn't just be one concept, or one part of a team. But yeah, if you guys have an opportunity to do cogen, don't do it. Great. We submeted chill water. The chill water, we go ahead and through efficiency and through what we can do pro rata share as far as service contracts and our labor to maintain the units, because in-house engineering doesn't, is $1.92 per ton hour. That's pretty expensive. So we could go ahead and cut, that's in the lease, and that could come back. So this is a great question, and it's something I can cap on. Now I'm going to go ahead and I'm going to go to tenants and I'm going to say, get your stuff out of here. Well, that's a lot of money. Well, what happens is that we have certain tenants that have 10-year leases, and the third year into the lease that will charge back $110,000 a year just for the cooling. So you're at 1.1, 1.2 at the end of that lease of nothing, right? You got nothing. So if I catch a lease early enough and I could show, look, you're going to go ahead and spend $300,000 moving your equipment down, right? I want you to spend that right now, because in the rest of your lease you could possibly save, $200,000 after all said and done with some charges. Because if we go ahead and go to that, again, from 25 cents per kW to cool that supplemental load down to 5 cents, I'm passing that savings on to the tenants. So that savings will go ahead and be an ROI to that individual tenants to move their infrastructure down. And I'm going to go ahead and give them new equipment and more redundancy, meaning the different stages of cooling, air, DX units, Sure, and then we have those things called server farms, right? Hey, IT people, you don't need to be on the door next door to your computers. You don't need to do that. So buildings don't allow that. So our lawyers, attorneys, went ahead and did not rewrite existing leases, new leases. So there's paragraphs in there that we have that option for future. Then we go back into existing leases, and just like a lot of things in leases, amazingly enough, all those words and the legalese, a lot of things, the lease is silent. So then what I try to do is develop an ROI for that tenant. So then what happens too is that, let's say the majority of tenants go, but that guy that 30th floor doesn't want to do it. Then we go, well, here's the cost of maintaining that. You want to bear this whole cost? Yeah.
More people come up.
Exactly. Right. So then don't be that last person coming out. So I set up the project. This is what I had to try to explain to my management. And, you know, back and forth is that, you know, we could kind of, quote unquote, a little bit strong arm though a little bit, but, well, we could do this. Yeah, exactly. So you build up to set the project up to succeed. Yeah. 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 Natural gas. Just life safety. We don't load shed and all that. Cogens, PG&E has a Rule 21. I don't know if everyone's familiar with that. Big three things on that is that I can't island power. I can't do that anyways. A blackout, let's say, but then I can't turn my gensets on and light the building up. Can't do that. I don't have load shedding capabilities anyways. And, you know, PG&E, you know, is pretty reliable, so it's fine. And then I always have to import in 100 kW at any given time because I'm guaranteed a PG&E customer. Thanks. And then what else can I do? Oh, I can't push back to the grid. So the grid's multi-layer, so they don't want foreign voltage coming in when they got hands on the grid. So yeah, like I say, take my card. Here's my email. Any questions? You know, a lot of times I could, you know, go ahead and provide a tour, you know, per se. So that's always a given there. We planned it enough. Thanks, guys.
I just wanted to indicate to the online attendees, if you do have questions, submit them to the chat window, and I'll make sure that Doug gets them. And we are recording this, and we can make that available.